It's enter, right? It's enter, or to move a slide, it's arrow down. Just this arrow. Okay.
Well, this morning, we're going to start this with our first talk from Simon and Radoslav. We talked a lot at the Birds of a Feather. I'll let them tell you a little bit about themselves and start their presentation. And thank you all for coming this morning. Simon?
Good morning. Thank you for coming. My name is Radoslav Szymanek. Currently, I work at the company CrossIntech, and today we'll present our collaboration with EPFL, with a rigorous system design lab, and Simon Blitz is from this lab. And we are also working with 2 PhD students. So it's an activity of 4 people for last year. And this project was sponsored by CTI, Swiss Commission for Technology and Innovation. So during this year, we're working on coordination. So today we'll be talking about coordination. And in this project, we applied BIP. So I will present the BIP background. And my colleague doesn't like to do self-advertisement, so I have to do it for him. So it's a framework that has been applied and a toolset that has been applied in an embedded design space. And what we're trying to do is the lessons which have been learned there to bring into Java. And this framework, this toolset is maintained and developed by Verimac and RIST. And it's 2 entities that are directed by Professor Joseph Sifakis, who is an Alan Turing Award winner. So there's a lot of knowledge, a lot of work which has been already done there over the years. And now for last year, we're trying to do it to bring it to Java. So now I pass the microphone to Simon, and he will explain a bit about BIP.
Thanks, Radek. So as Radek just said, we're talking about coordination, and we're talking about coordination for concurrent components. So to start with, to get you warm, why are we actually talking about coordination? So the point is that nowadays, the real-life applications run enormous numbers of software entities. I could say components, entities, whatever. And when I say enormous, that's thousands or hundreds of thousands. And these entities, they share access to resources, right? Like memory, bandwidth, thread pools, whatever. And when you have hundreds of thousands of entities sharing access to resources, that gets complicated, right? So both communication and data exchange can be quite complex. And if you do not manage this, well, that could lead to disastrous results. Because essentially when you're saying coordination in this context, you mean concurrent access to resources, as I said. You mean mutual exclusion. And this has to be managed, right? Otherwise, you'll get something like this. And this management of mutual exclusion is essentially some form of synchronization, right? Because you have to fix the logical time, whether the components are trying to access the resource, and then decide who actually can access that. So we're talking about synchronization. Now, the plain old way of doing synchronizations is by using the operating system provided or hardware provided primitives like semaphores, locks, etc., you name it. And this gets quite nasty, right? So here I have a very simple example. Like that's a basic. So that's what I'm sure you all know it. Actually, probably better than I do. A synchronization barrier. So we have 2 threads, 2 tasks, which have to synchronize. And how we do it? Well, we take 2 semaphores, S1 and S2 here. We initialize them to taken. And then the 2 tasks, they will free and take them in a particular order so that at this specific point, they kind of will be waiting for each other. And they will be forced to synchronize. So that's nice, clean, and simple. Everybody understands that. That's the same thing for 3 tasks, precisely the same thing. And what we see here, it's not. I would love to say it's exponential. Here it's quadratic, but I mean, it grows non-linearly. And this is already, I mean, you understand what it is, right? But it's kind of more difficult to grasp. If I showed this directly, you would have more trouble. Now, of course, we can do even worse than that, right? We can. Here, what I've put here is a real-life example in the sense that it's not just synchronization, but a synchronization barrier for the sake of a synchronization barrier. These here are two synchronization barriers, and then around you have some functional behavior because you do synchronization barriers to do something, right? And here, I mean, you don't have to read the actual meaning of the code, but the idea is that, okay, you do some initialization on some data, then you do some data-dependent operation where you're actually doing some exchange, right? And you want this exchange to be coherent across the two tasks. So what you do is, well, you synchronize them, you do the operations, you resynchronize at the exit because, well, then you'll be using this data. They have to be up to date. And then you do whatever you want to do. Now, well, this is still kind of nice and clear because I've put the red boxes around the synchronization barriers. I'll remove them. OK, so we still remember what that means. Now, 6 months from here, you go back. I bet even if it's your own code, or maybe if it's your own, it's well commented. But I had to do it. Where when you get to somebody else's code, which looks like this, it's not commented, you'll spend 6 months understanding what it does before you can actually fix it. So my point is, code maintenance is a nightmare when you actually try to use low-level primitives. And what we have to do, if we want to do synchronization in a smart and scalable manner, is to raise the abstraction level. So rather than using low-level primitives as here, we have to use something else. And here's where BIP comes in. So BIP, well, it stands for behavior, interaction, and priority. And the point here is that there is behavior, which is functional behavior of the components, which you see essentially here. And then there are interaction and priority, which are coordination glue. So here they're materialized by these green connectors. I will not go into detail of the semantics of these connectors, although there is formal semantics for them. The only important point for us here today is that they essentially define synchronizations. And what do they synchronize? Well, as I said, we have component behavior here. And as you can see, this component behavior is modeled by finite state machines. Right? In these finite state machines, you have transitions, which are labeled by what we call ports. And the ports form the interface of the components, right, here and here. And the connectors, they define the synchronizations between ports. So essentially, synchronization between transitions. And this essentially gives you the abstraction layer, rather than saying, OK, I will use a lock here, a lock there. And you say, OK, I'll synchronize that, that, and that. So it kind of gets much simpler to reason about. And the main point, we're doing separation of concerns in the meaning that we separate the functional behavior from the coordination glue. And this coordination glue can be changed without touching the components, without going inside and modifying the code. And I think this is very important. Just a quick slide to say, OK, we did not invent the finite state machines. We are not the only ones to use the finite state machines. They're all over the place. And we're just doing the same thing as everybody does. We're just, the thing we're doing, the thing we actually invented is the way you do the coordination, the glue part. So that's why we focus on the coordination in the talk. OK, now here is the meaty part of the beefy part of my part of the talk. That's one slide to explain you what BIP is. Right, so I already said that there are components and there are connectors. Let me explain a little bit more detail. So here, what you see in the top part of the slide is what I call the design front end. So that's how you look at the system when you assemble it, when you manipulate it, when you do whatever you like with it. You see components, and separately you see the glue, you see the connectors. Here in the bottom of the slide, I call this semantic backend. So this is something which we never compute. We do not manipulate that. This is just here to explain what we mean, right? So what the entire system means. OK, now to the example. So here we have two components. They're absolutely the same up to port renaming. Here is B1, F1, B2, F2. And these components, they just provide you a high-level, very abstract model of a process, right? And this process, what can it do? It can do some work. So it has two states. In one state, it is not working. In the other state, it is working. And the transitions are correspondingly named begin and finish. That's where B and F come from. And as I mentioned before, typical example is mutual exclusion. We do not want these guys to work at the same time because they share some resource. Okay, it's an academic example. Could be process, could be memory, could be whatever you like. So what we want to achieve is something like this, right? This is the product state. So there is a state where none of them actually works. There is two states where only one of them works, and then there is a bad state where both of them would be working together. And we want this state to be not reachable. So that's exactly what you see here. Unless you start here, you will never get here. You can see it right away. And then between the three states, you can go around in different manners. That's not my concern. I'm only concerned with safety. Okay, so if we do not do any coordination, that means there are two components running in parallel, doing whatever they like, right? And that's what you see here. Like, anything might happen. So there are all the transitions like begin, finish separately on both sides, or synchronizing together. We do not control anything, right? They could happen at the same time. So it could happen that both of them begin together and just go directly to this work state, and then it crashes, right? And that's where BIP kicks in. We specify the coordination. We specify what these guys are allowed to do in collaboration, right? And there are two levels, layers, as I said, interaction and priority. So the first layer here is what we call the interaction model, and that's essentially what's specified by the connectors. These are all legal, allowed interactions. So here you have begin, finish of both components separately, and I can authorize the begin of one synchronized with the finish of the other. So if one is ready to finish, the other is ready to begin, well, they can do it together, I don't mind. Okay, so that's for the sake of example again, right? Symmetrically. So that essentially, applying these constraints to the two components, take us from here to here. It removes the vertical transitions. It disallows the simultaneous begin of the two components, and it disallows the simultaneous finish, but who cares? And then there's one more thing to ensure. Okay, if I want to ensure mutual exclusion here, what essentially I want to do, what I'm saying is that one component is working, which means that it actually can finish, and the other one is not working. It can begin. Well, I would prefer finish to begin. There's some kind of priority. So here, I'm saying that I will prefer, when I said if one is ready to begin, the other is ready to finish, so I can have this begin and finish together. So I would say, well, if they can do that, I will not do just begin. Right? So we call it here maximal progress. It's a special case of priority, but we'll not go deeply into priority, actually in more detail. And this, well, you can see, if you like, probably I'll skip it now, but we can show it later. This priority actually removes the last two transitions here, which are bad transitions, right? And we obtain precisely this nice model. So to summarize, we have two components. We impose coordination constraints separately, and we can actually synthesize these guys, but that's a separate detail. And by imposing these constraints, we force them to work in the proper manner. Now, the question is, OK, how do we actually force them? Well, we use an engine, right? So we have the two components running, and then there is a BIP engine, which actually does the coordination. And this happens in a two-phase protocol. So there is the first step, the components actually do their computation, reach the states which were shown in the finite state machine, and then they tell the engine, well, here is what I can do. And the engine collects all this information from all the components, and it knows the interaction model, it knows the priority model, so it filters all the forbidden stuff out, and among the legal one, it just picks one and say, well, now you do that, you do that, you do that. The other guys, you wait. And that's it. Simple as that. Now, to the OSGI. So I said, well, to do that, we need a finite state machine, because that's what we're doing, right? OSGI actually has a finite state machine associated to each bundle, but for a good reason, all the functional states are actually, they're not shown, they're here. Like once a bundle is active, it's active, and we don't know anything more. And the good reason is that this is actually semantic information. OSGI by itself cannot know it. The developer has to specify it, has to tell it, because the developer is the guy who knows what the states are. And that's actually what we will be doing. So here I'm passing back this to Radek, who will explain how it works.
Thank you, Simon, for presenting a bit of BIP. And hopefully now you understand why we need coordination, why we do it the way we do with a BIP. And now I'll try to present a bit of use case, a bit of code, so that you can get a better feeling as developers how it works. So I have just, let's say, half of marketing slide. So in CrossIntech, we have a product which is called Connectivity Factory. What you need to know is an OSGI container, okay? And what you need to know, we use a lot of open source software. And we use the software to help our clients to integrate their systems. And one of the software we use a lot is Camel project from Apache. So Camel project from Apache, it allows you to do integration. It allows you, for example, to take the data from system A and put it in system B with some transformations. So now if you have a lot of systems, you may have a lot of routes. And what happens is that if you have many of those routes which are actually running within OSGI container, each of them may take a lot of memory, and then if you don't have a coordination, the things will start to break. You will get out of memory exception. So we really have to focus on coordinating things which originally were not necessarily meant to be coordinated together, just because they run within the same OSGI container. So what we can do is, for example, one simple thing is we have 100 camel routes, and we may want to remit it to maybe a safe number, let's say 50. So if all of them 100 are running, you would just run out of memory. And this is a very simplistic use case, just to show you a bit. It doesn't mean that this is just the only scenario. So it doesn't mean that the work we did is only applying to Apache Camel, no. It doesn't mean the choices, the technological choices we made, doesn't mean that you have to make the same choices. It's just a use case, just a simple example to show you visualize. So, a bit about Camel. In Camel, what you have routes. So you have a route builder. So a route is something, an entity that you declare what it should do. You declare that it should take something from a system A, it should do some processing and put it in system B. So it is important that you actually declare. You have a route definition that you specify what you want to have it done. And this is, let's say, the end of your coding. You don't really have more than that. What you can do, you can assign identity to this one, a root ID, and through this root ID, you can use it within Camel engine to actually tell things to do with that root. For example, you can use suspend root to suspend the root, and you can resume root to resume it. So you have an entity that is actually declared and that is executed by the engine. And now you want to actually coordinate that entity, to which you have very little control of, and only through the API which already exists, the Camel engine API. So how can you actually do it? So the little problem here is that if you look at the state machine here, what you have a working state and you have ready state. So when the root is ready to be executed, it's on, but there's no, for example, there's no file which has been dropped in a file folder, so there's no processing. So it's just ready, it doesn't use memory, it's just waiting for things to happen. So then when somebody drops a file, then the root starts to work, so we have a begin transition and we are in a working state. So in this state, we can be using a lot of memory. Just because we want to be efficient in terms of processing, we'll take a large chunk of the file, we'll do some processing. So in this state, you're actually using the memory. So now, if we do a transitions like suspend root from here or from here, we're actually in two different stages. Here we are suspended and we are not doing anything. Here we are in the process of finishing, but the things we are doing, we are still doing. So here and here, are actually quite much different in terms of memory usage. So what we have a real problem here is that if we are in a ready state and we tell the Camel engine, please stop, so we do an off thing, there is a race condition. There is a race condition between our order to stop and somebody putting a file. We don't want to have these race conditions because at the end, after we execute the off, we don't really know in what state we are. It's quite a difference between here and here. So this kind of model is not good for coordination, good for understanding what is happening with our model. We have to change it. Okay, so here we have two different types of transitions. Enforceable, the ones which we can enforce, and spontaneous, so the ones which happen just because of environment. Okay. So now, how do we do the little changes here? So first of all, you have to take this, your model of the camera route, and you have to transform it into something that is beep proper, and that allows you to do a coordination. So what you notice here, we are in an on state, and we do enforceable transition off. So we're no longer immediately in the off state, we are getting to the wait state, from which we can have two different transitions. An end, which is we are told by camel that the current exchange has been completed and that you have finished processing. So this is spontaneous transition, which we being informed from the camel engine, or internal end means that we are done. And here what is important, that we have guards, which are functions that you compute to tell you which transitions you are taking. So we don't have here race conditions because we have mutually exclusive guards. And then we are done, and then we can do finish. So now if you look at this beep monitor, this is a part where we actually are about specifying what is allowed in the system. So here you see that we have finite state machine again, and this is a part which you add to manage the system, and you say that I allow transitions, but I allow only two camera routes to work. And then if I add, I'm moving to the right, and if I remove to the left. So the interaction, what happens here, if you look at odd and add, this is an interaction. So if we had an on from here to here, we actually have to do at the same time an add. So we are synchronizing components that we want to coordinate with the beep monitor. So we're using beep framework to make sure that we have a safe system, meaning that you don't have too many routes. Okay, so now a bit of code. Soon, just still a bigger picture. So exactly as I said before, it doesn't mean that you have to use Spring. I'm just using an example. So in Spring, you have a Spring application context, and you have multiple beans, and some of these beans may be camel routes. So you have here to the left the camel routes, which you want to control. So now what happens is that you create a beep specification that actually is for controlling that camel route. So here we're using camel API to control the behavior of the route. You take this control specification and you feed it to what we call beep model executor, is an entity that is responsible for making sure that the coordinations is done in a beep way. Okay, so developer has to write only this part. Has to understand what is the finite state machine of the component he wants to coordinate, control, and then write it as a Java class. So the beep spec is actually a Java class. And here, the administrator, for example, may create a beep monitor specification, so how the system is supposed to behave, what is allowed, what is not, and then the beep engine does the coordination. So the components inform the beep engine what they can do, and then beep engine tells them what to do. Okay, so this is a big picture overview. So now finally I can get to some code. So here is our class, switchable route. So we want to have ability to control camel routes. So we want to have ability to switch it on and off. And this is a specification, so Java class, which is a specification. See, we can use here things like from Spring for initialization, so we can inject anything we need to our beep specification to actually be able to control. So one thing we'll be injecting is camel context. Okay, so here what we say, like we talk about behaviors. So one thing we have to do is have to specify ports. So we have an off port and end ports. We have annotations to this class, which will say, okay, we have a port end, which is of type spontaneous. So there's somebody else, entity from external, which informs us that there was an end transition. It's something we may want to take care of. And there's also an enforceable that we can actually switch it off. So this component may allow an off transition, something we can enforce. So there's this distinction between spontaneous and enforceable transitions. So here we have a finite state machine, we have ports, and this is what is actually being described through this class. So we're using Java class as a means to specify the finite state machine, the coordination mechanism, and how the whole this thing which were presented before in the beep. Okay, so transition, another annotation. We say that we have a transition off, which is, for example, here, which goes from source to state on and it goes to target wait, and doesn't have a guard. So there's no function which has to be computed to true to actually allow this. So we can do it at any time, as long as we are in state on. And what is interesting here, if you see, we have a function that is being executed from the specification to actually execute this transition. So here we are using camel context. So we are using the camel API to actually manage our entity that we want to manage. So here we are just using suspend root, and we give a root ID to do the suspension. So we are executing the off transition here. So we talk about transitions. What is important, we can have guards. Guards which tell us if a transition is enabled or not. So here you see one transition that has a guard is finished, and one which is a negation of that one. Okay, so nothing changed. We still have functions. The important part is that we have guards now, and how do the guards look like? Simple, it's just yet another function. Okay, and here in this function, in the guard, we're also using camel API. So we are asking camel here, do we have anything in flight? Is there any things which are being processed by the root? And depending on the answer, we know that which transitions we have to take, either this one spontaneous, which we wait for information from camel, or we just take internal one. And there are guards here. Okay. So a bit about interfaces. So the first interface which I want to discuss is the BIP component. BIP component is a component that, first of all, can be told by the engine to execute a port, or can be informed by external parties about some spontaneous transitions. That's all, just two functions for coordination. Execute something that you have told us before that you can do, or just being informed about something which has happened. One part which is important here is that in this inform part, sorry, in the inform, okay, no, let's do it a bit later because I will confuse you. So here we have an executor, which I mentioned. This is a part which takes the BIP specification and makes sure that it's actually being referring to BIP standard. So this is everything that is about BIP, and make sure that the developer doesn't have to know much about BIP. It just has to know how to create a specification. So this is all the things which are taking care of connecting to the BIP engine for the BIP protocol and things like this. So here we have, for example, things like publish and publish. This is the OSGI registry so that the component is visible. Register and the register is to connect to the BIP engine, so the entity which will be governing. Again, very simple. Okay, one tricky part. The BIP specification, or let's say BIP component, has to get information from the external world about spontaneous transitions. How we can do it? We can use Camel API to create notifiers. To tell Camel engine we want to be notified when the exchange has been done, when the root has finished a piece of work. The little problem is that you have to actually inject executor, BIP executor to the BIP specification because it's an executor that has to be informed about it. So there's a little trick here going on. So there's not just executor knows about specification, but also specification about executor if you need spontaneous transitions. Okay, so conclusions. We really want to separate coordinations from the code. So coordination is done with things, the connectors, this is done separately. It's not in the code, it is in a separate coordination specification. This is something that, for example, administrator may want to do. He has an OSGI container, he wants to know, he doesn't want to have more than this amount of roots running. Okay, so we don't really have this coordination code inside. We didn't talk about this coordination code with BIP glue, we just have too little time. So it is something that is separate, it is something that we are allowed to change without changing the code. So, what about developers? This is our constant struggle. My point of view is developers' life should be easy. Then I make them to do more work because we have to do BIP executor, because we have to BIP engine. So developer has to only write BIP spec. So he needs to write only Java class. Java class that explains final state machine and explains ports. He has to understand the BIP semantics, BIP, let's say, attitude, BIP opinion. But when he does this one, he can do it very well. He can describe the final state machine of the components he wants to manage. He can manage components that even don't exist in terms of code, which maybe you want to use aspect-oriented programming. You cannot do in this case of a camel, because you don't really have a code. We just have an entity that is being interpreted. BIP specs are reusable. You can use it from one project to another. You just have a specification of the component you're using again and again. And you have this BIP executor that makes sure that you follow the BIP semantics, that the whole protocol is being respected. Okay? So a bit of the future work. This is yeah, I'm finishing. This is the last slide. It's about adding data transfer so we can do a bit better models. It's about using the things we already have, like transaction support. Interaction is something that has to happen in an integral way. We can use transaction support to actually allow to have it done in a bit better fashion. We want to do a more experimentation with real life. So for a moment, the only developers that are complaining is the developers from CrossIntech. We need more feedback and more people complaining, we want to do this and this way. And what I hope is that we will manage to get you interested with an OSGI community, and then you come to us, we have discussions, and then maybe we can add it to an OSGI standard. How to do the coordination. And this is it was our initial goal, starting from the beginning. And this is, I hope that we will manage to make it interesting for you so that you can come. Feel free to come and ask us during lunch. After the presentation, we are here, and you're free to discuss. So thank you, and if you have any questions, we are welcome. There's one.
Basically, you showed us that you're using this with Camel and Spring. Camel and Spring have most similarities in that they are kind of fixed up at the here. I mean, if I wanted to use this in my own tiny little application that doesn't have any of those technologies, but just I wanted to use a pure API, can I do that as well?
Yes.
No.
This is what I wanted to make sure. The use case and the technological choices is just because of the company I work for, right? So you just need to have a BIP engine. You just have to have a BIP executor. And you have to have your own BIP spec. Right. What is nice is that in the BIP spec, you want to inject things, right? So kind of dependency injection approach is something nice, right? So you may want to use one or the other, right? But it doesn't have to be Spring. We are trying to avoid XML as much as possible. So we are using BIP spec, which is a Java class, not an XML. And so we are trying to stay within the Java class within the code, something which developers are familiar with. So we really are trying to make sure that you are not constrained by our choices. The only thing you have to understand is BIP, how it works, how the coordination is done, how you specify the coordination glue, nothing else.
Any other questions?
Thank you.